Before I'm going to define the Fock space, we should also think about how to address the fact that we only want to consider a symmetric subspace of the Fock space. We want vectors where we can commute the tensor, the elements in the tensor, and so we don't want the full Fock space. We don't want the direct sum of the tensor of all tensor powers, but we only want the symmetric subspace. And in a Hilbert space, it's always a good method to get a subspace by having a projection which projects onto the subspace. So we should have operators which implement the commuting of the factors in the tensor by operators. And so that's what I want to do. And maybe I put the main information about this in the following theorem. So we construct operators which commute the factors in the tensor according to a given permutation. So let us look on a permutation, sigma in Sn. Sn is the permutation group on n elements. So sigma should be a permutation of n elements, let's say 1, 2, up to n. So that's our numbering of the factors in a n-fold tensor. And then I want to define an operator which commutes according to sigma the factors in the tensor. And in the tensor product, guys are given by linear combinations and also maybe infinite linear combinations. But of course, it's enough to define this essentially on one elementary tensor. So then we can extend, and that is clear how we should define it. So I want to define an operator which I call u sigma, and if I'm acting on this on x1 tensor up to xn, I'm just exchanging the factors here according to sigma, and I do this in a way that I take here the sigma 1 x with the index sigma 1 and so on, x sigma 2 up to x sigma n. So I'm actually exchanging the indices of my tensors. I could also exchange the positions. This would be essentially doing the other way around, but maybe it's best for us to do it in this way. So I'm numbering things here from 1 to n, and then I'm rewriting the terms in the form sigma 1, sigma 2 up to sigma n. And so this is defined on elements like this. Then I have to take direct sums, or I have to take linear combinations of elements like this, and of course this here extends to this, and then it should also extend to the completion because everything is continuous here. So that's the main statement here. So if I'm defining it like this, then this can extend uniquely to an operator on all of the tensor power of my Hilbert space. So u sigma is an operator on h to the n, and of course it goes to h to the n again, because this is again element in the nth tensor power. And of course this u sigma is not just any arbitrary operator, but it has of course very nice properties. So in particular it's always a unitary operator. For all sigma. So u sigma is unitary, so in particular also bounded of course then. And we have, and actually the behavior in sigma is the same as sigma. So in principle it's a representation of the permutation group. So what we have, of course I can consider u sigma tau for two permutations, and this is then u sigma times u tau. So here I'm taking the product in the permutation group, and here I'm taking the product of the operators. So we have this, of course, for all sigma and tau permutations. Then maybe, of course, it's also clear if I take the identity permutation, where I don't permute anything, then it's clear that this is just the identity operator, because then I have here just 1, 2, up to n. So this operator doesn't do anything. So the identity permutation, the corresponding operator is just the identity operator. where, let me say, with identity here, I mean the identity permutation for the identity permutation it in Sn. Yeah, maybe it's also good to think about so what is the adjoint of U, and I mean, of course, according to this, it's clear what it has to be, namely it's just the U of the inverse of my permutation. So if I take U of sigma, so and I take the adjoint of this, then of course, yeah, then because U is unitary, this must just be the inverse of U, and so according to this means that this of course must be U of the inverse of the permutation, which of course is also very easy to see directly. Yeah, okay, so that's the main properties I think which we need and which are very easy to see for this representation of the permutation group. So this is a very nice and also important way of representing the permutation group on such tensor product spaces. Good, now we have to use sigmas, but what we want is now actually a projection operator, which projects onto the symmetric ones. Of course, each U sigma is just permuting the factors. So the U sigma doesn't allow me directly to say whether I have a symmetric tensor or not. Of course, symmetric should mean that if I do any permutation, I get the same operator. I get the same vector. So what I should consider is now an operator which sums over all these U sigmas, because this operator can then check what happens if I'm permuting my factors in any way. Good, so that's maybe the main object we want. So namely, I define operator. So for fixed n, so I mean n is here arbitrary but fixed. So let's say n is fixed here. So I'm acting. I have to use sigmas for the sigmas from the permutation group Sn, and then for this I can define my operator Pn, some normalization, which is n factorial, and then I'm summing over all sigmas in the permutation group over those guys U sigma. And now I'm claiming this is really what we want. This is an orthogonal projection, and it projects down onto the symmetric tensors. So this operator is an orthogonal projection on H tensor n, and it projects really down onto the vectors which we are interested in, namely the symmetric ones, and projects onto the symmetric tensors. And maybe I should say what I mean with this exactly. So the symmetric tensors are those tensors which don't change if I act with any permutation of them. So I can exchange the terms as I like, but nothing happens. So I'm claiming here that if X is in the image of Pn applied to H to the tensor power n, this is the same as that any U sigma acting on X doesn't change X. So this is X again for all sigma in the permutation group. So I mean this condition should, this specifies what I mean with symmetric tensor, and here I'm claiming that this projection really projects down onto them. Good, okay. So maybe just to make clear, a symmetric tensor, of course, in general, is not such an elementary tensor. Of course, if I have X tensor X, this is symmetric. But if I have X tensor Y, this is not symmetric, and then I have to add plus Y tensor X. This is a symmetric tensor, because if I exchange here position 1 and 2, this will go over to itself. And those are the guys which are in the image of Pn, and which satisfy this property here. Yeah, okay, so this is the statement. So let us prove this. This is more or less all should be easy and clear. Few calculations, and maybe in the first step, the main point is of course this unique extension, and maybe for this one has to note that if I have a linear relation between the axes, because I mean I have to extend this from this to linear combinations of this, and of course the problem might be I have a linear relation which is equal to 0, but if I apply this u according to this, it's not 0. But this is the thing which one has to notice, that this cannot happen. So one has to note that if I'm summing over I of, so if I take a linear combination of tensors of the form x1 up to tensor xn, and I have several of them, so I'm putting index I here, and I'm summing over them, and this is equal to 0, then of course this still should be 0 if I'm applying my u sigma here, which means I'm exchanging the indices here. So this should imply that if I'm now taking the sum over x sigma 1 I tensor and so on x sigma n I, that this is still equal to 0. Okay, but this is easy to see if you just apply your inner product, because I mean something is equal to 0, you can check this, or this is equivalent, that this guy with itself, the inner product of this guy with itself is equal to 0, and now we know how to calculate the inner product in a tensor product, and then of course you just have to see that if I'm exchanging the terms here, it doesn't change this equality, so that also the inner product of this with itself is equal to 0. The inner product of this with itself is the same as the inner product of this with itself, just because the inner product really it's just the product of the individual inner products, and of course there you can exchange the order. Okay, so anyhow, this is easy thing which one should observe, which then allows to extend this to finite sums, and then maybe it's good to know that you have a unitary operator, or at least a bounded operator, so that also if you go to infinite sums, this is preserved. But to see that you have a unitary operator is actually maybe the easiest if you just check that actually if you take the canonical basis which you have in this space, that under this operator this is mapped onto itself. So I mean a unitary operator is one which maps an orthonormal basis of your space into another orthonormal basis of your space. But in this case, the other orthonormal basis is just a renumbering of the ones which you already have. So maybe that's also something which you should observe for this statement, and then which also makes this extension clear. So that. So if we have, as we know, if I have an orthonormal basis of my underlying Hilbert space H, let's say from 1 up to D of H, then we know how to get an orthonormal basis of H to the n. Namely, we just take arbitrary tensors of all those guys here, and now one just have to see that U sigma maps this orthonormal basis to itself. Because it just shifts the indices around, and this is then again another element in this basis. So U sigma maps the orthonormal basis of H to the n, which is given by e to the I1 tensor e to the I2 tensor e to the In, where these i's here are just running all from 1 up to D, and this, so if U sigma acts on such an element, I just get again a product of the e's, only the indices are now reshuffled. But of course then I still have something which is in this set. So this is mapped, so this orthonormal basis of H to the n is mapped bijectively onto itself. Bijectively onto itself. And this means the U sigma is unitary. Yeah, good. Okay, so that's part 1. It's maybe Small details you can check for yourself, which are still left, but essentially this tells us about u sigma, and then of course those guys here, this things should be clear. So you should check this for yourself. But now let us look maybe on a more interesting one, part 2, namely first that this Pn really is an orthogonal projection, and again, we can check the property being orthogonal projection just in algebraic terms, because it just means that it must be self-adjoint and the square of the operator must be itself. So, and we have all those algebraic properties which allow us to do this in a purely algebraic way. We can forget essentially, maybe the concrete action on the Hilbert space. Okay, so first let us check that it's self-adjoint. So what is Pn star? So we just take the definition, so it's 1 over n prime. Then we are summing over the permutation group, u sigma, and now I take the star, and of course this means I have to get the star here. But if I'm taking u sigma star, what we have seen before is that this is the same as the u of the sigma inverse. So this is now 1 over n factorial. I'm summing over sigma in Sn, and now I have here u, not of sigma, but of sigma inverse. But of course, if sigma is running through the permutation group, sigma inverse is also running through the permutation group. So I'm still summing here over the whole permutation group, and I'm taking u of all those guys. So this here is nothing else than Pn again. Good. Now let us look for Pn squared. And of course there I need this normalization. So for this argument I don't have a normalization, but of course it's somehow clear 1 over n factorial. N factorial of course is the number of terms which I'm having here. So I'm really take the average here over the u sigmas. Okay, but let us see. So Pn squared, so what is this? So I'm just writing down the definition of the Pn twice. So I have 2 times the n factorial, and then I have a sum over, let's say, sigma in the permutation group, and from the second Pn I have a sum over, let's say, tau in the permutation group, and I have u sigma times u tau. But now we know the u is a representation of the permutation group, so this here is the same as u sigma times tau, and now, again, so let's say, if I only look here, so I'm fixing sigma, and then I'm running with tau through the permutation group. But if tau is running through the permutation group, then sigma tau for any fixed sigma is also just running through all the elements of the permutation group. So again, in this sum here, I'm just summing again over my permutation group, let's say pi. So maybe let me call this here just pi. So I'm running over the permutation group, and I have u pi. Okay, so what I get here now is actually I have, let me write it down, n factorial, and then for each fixed sigma I just have the sum over pi in Sn running over all u pi, but this is the same for each sigma, so I just get this here as many times as I have sigmas here, which is n factorial. And now you see 1 n factorial goes away, and I'm just left with the definition of the Pn, summing over all pi's, taking the u pi, and then normalizing it by 1 over n factorial. So this is Pn. So we see that really we have here an orthogonal projection. And now, last thing to do is to check that it really projects down onto the guys which we are interested in, namely the symmetric tensors. So for this, we're claiming that being in the range is equivalent to being invariant under the action of all sigmas. So let us, we have to show 2 directions. So start with that we assume that u sigma of x is the same as x for all sigma in the permutation group. So we assume that x is invariant under the action of any u sigma, which means x is a symmetric tensor. But what does this mean for Pn? Then of course Pn of x, so this is 1 over n factorial, then I'm summing over all sigma, and I take all u sigma, and I apply this now to x. But according to my assumption, u sigma acting on x is always x, independent of sigma. So I get here, so I get here x, and I get this for each sigma, so I get it n factorial times, but I'm multiplying by 1 over n factorial, so this goes away, and this is just equal to x. Good. Now the other way around, suppose that we know that x is in the range of this projection operator, and then I want to see that it is invariant under the action of any u sigma. So okay, so let me take u sigma acting on x. I want to see this is equal to x. Yeah, but so the x, of course, I can now also write as Pnx. Yeah, and then what we already used before, or what is easy to see, is that if I'm multiplying the Pn with any u sigma, this just gives me the Pn again, because that's what we did here. So if I'm still running, after multiplying it with a u sigma, I'm still running over the whole permutation group. So this here is just the Pn again, but so what I have here is Pnx, but by assumption the Pnx was equal to x. So this here I get, and this is true for all sigma in the permutation group. So if x is in the range of this orthogonal projection Pn, then this means that it is invariant under the action of any u sigma. So it's really a symmetric tensor. Yeah, so that's the end of the proof, and so this means we have now a very nice and clear idea of how we get the symmetric tensors in our general tensor power h to the n.